All right, let's resume our discussion. What we will do next is actually discuss one more operation and connected transformation known as minimum cardinality. This is actually not part of the set of operations that we mentioned before and which appear in the original knowledge compilation map, but it's actually pretty important and has applications in a number of places, including diagnosis and explainability. But this time you're going to help me with this. This time you're going to discover the algorithm for me. I will explain to you what is the task, and you will tell me how to do the linear time traversal on the circuits so that I can solve it. So let's define this query of minimum cardinality. Let's say I have a knowledge base like this one. We've looked at this. And if you go ahead and look at the models of a knowledge base, right? So in this case, I have 5 variables. So I do have 32 possible instantiations. And some of these are models of this formula. Now, this query is defined as follows. You look at the models and assign a cardinality for each. And the cardinality, as we're going to define it, is the number of variables that are set to false. Okay? You could have defined it the other way around as the number of variables that are set to true, but we're doing the false because that's typically what ends up being used in some of the applications we're going to talk about later. So for this particular guy, what would be the cardinality in that case? In this case, the very first one, if this is a model 1, very good. And then the second one will be 3. So what this query wants is the minimum cardinality attained by any model of the formula that I have or the knowledge base, right? So if you want to do it without worrying about efficiency, you'll have to enumerate the models one by one and check the cardinality of each and then take the minimum of that. That's what we call the minimum cardinality of the Boolean formula. You'll see later, for example, this can be used to say if a device is not behaving normally, that means something broke. What is the minimum number of components that could have broke? Okay, that's one of the simplest things, but it has many more applications beyond that. So the claim now is this minimum cardinality can be computed on decomposable negation normal form in linear time. And I want you to help me discover that algorithm. And remember what we do for these algorithms. They are one-pass algorithms. That means you start at the leaves, you assign values to the leaves, and then you move up, doing some computation on OR nodes and doing some computation on AND nodes. And like we did before, when you're looking at the leaves, these are independent problems, right? So you think, when you look at a node, you are only thinking about the formula represented by that node when you're deciding what is the right answer. You forget about everything else in the circuit. Okay, so let's start at the leaves. And let's pick this guy. Assuming that's it. This is your knowledge base. There's nothing else. What's the minimum cardinality of that? Someone is saying 0. We're looking at not X and not okay, Y. How many models does this have? How many models does this have? This has actually only one model. The only way to satisfy this formula is to set okay, Y to false, correct? This guy has only one model. Similarly, if you look at this guy, it says not A. The only way to satisfy it is to set A to false. So it also has one model. If you look at this guy, it only has one model. C is true. So let's ask the question again. And remember, when we did cardinality, we counted how many negative variables are in the model. Okay, that's what we did. So we look at this guy. What's the cardinality of this guy? The minimum cardinality. Okay, now people are saying 1. Because there's only one model in this case, and that model has a negative variable, so it's 1. What about this guy? What's the cardinality, minimum cardinality of that? And people are saying 0. Very good. 0. Okay, so we figured out the literals, and You can basically go ahead and do that here. The positive literal are getting 0, and the negative literals are getting 1. Now, all we need to do is, okay, I'll get to the true and false in a second, but let's skip them for now. Then we have to just figure out what to do at OR nodes and what to do at AND nodes. So let's start with OR nodes. And you have to tell me, how do I compute the minimum cardinality of an OR node if I know the minimum cardinality of children? So let's look at it this way. I do have alpha or beta. Let's call this whole thing gamma. I give you the minimum cardinality of this, and I give you the minimum cardinality of that, and I want you from that to compute the minimum cardinality of this guy. Okay, I already have one answer that says take the minimum. Okay, and indeed that is correct, but let's see why is that the case. You have to think about what is the minimum cardinality of this, right? I'm looking at the models for this guy, and I want to do what? I want to find the minimum cardinality that any of them can attain. Now, what are the models of this guy? Now, we know this from before, right? Mods of gamma is what? Is mods of alpha union mods of beta, correct? Now, I already, by giving you the minimum cardinality of this, I told you what is the minimum cardinality attained by any of these guys. And by giving you the minimum cardinality of this, I already told you the minimum cardinality attained by any of these models. So just take the minimum of these two guys and you get that. Okay, so let's do that. And if we do it here, this is what happens. This guy, minimum of 1 and 1, minimum of 1 and 1, minimum of 0, dot, dot, dot. Okay, we got it. Now we get to the last case. We do this case and we basically figure this guy out, which is effectively, I have gamma equals alpha and beta. I gave you the minimum cardinality of this. I gave you the minimum cardinality of that. What is the minimum cardinality of this guy? And remember, what we have is decomposability. These guys cannot share variables. Okay, so now I'm getting a number of answers. One of them says take the maximum, and some are saying take the sum of them. So I have two answers, either sum or max, either sum or max. Let me show you an example here. Let's say this guy happens to be the variable A or B, and this guy here, it's decomposable, it's probably not C and D, okay? That's what's going on. Now, what you need to think about is the models of this guy in terms of the models of these, and then you should be able to figure out the answer. In the OR, what did we do? We took them and union them. Now, in this case, a model for this guy is a variable instantiation of the variables A, B, these models. In this case, the models of this guy are instantiations of C, D. Now, how do I get a model for this guy? I take a model from here and a model from there, and I paste them together, and then I can get a model for that guy. So if you want to think about it as a combination, the models for this guy is like the Cartesian product of the models of this and the models of that. Now, with that observation, what would you suggest now? Is it a max or is it a sum? And someone is saying it is a sum because they are independent, they don't share variables. Indeed, it will be a sum, right? Because you're gonna get, I'm giving you the minimum cardinality for this guy, which tells you what is the satisfying assignment that has the smallest number of false variables. And the same thing for this guy. When you put them together, you have to add to get it for that particular guy. And so if we do the summation, we get this. And what this tells you is for this formula or for this circuit, if you look at all its models, all its satisfying assignments and check the cardinalities one by one, you will find a model that has a cardinality of 1. And every other model will have either a cardinality of 1 or more. That is, there is no model for this formula in which all variables are true. And actually, it turns out you can even do a little bit more than this, which is Fine. You come and tell me here's a circuit, and you tell me the minimum cardinality is 3. What does that mean? That means every model has to set at least 3 variables to false. Well, what I want is I want to be more ambitious. I want the minimum cardinality models, the ones that have attained the value 3, captured as a DNNF circuit. And I want to throw out all other models. Again, this ends up being useful in certain applications when you want to throw out unlikely scenarios and reason only with the likely scenarios. And it turns out you can do this by simply killing some of the edges in the circuit. And I'm going to show you the numbers for min cardinality, and maybe some of you can guess. If I were to throw away those models that do not attain minimum cardinality, what edges should I kill? And you have to remember, anytime you're thinking about a node in a circuit, you think of that node representing its own little circuit, its own little formula. So let me make this maybe a little easier on you. Pick this node, this guy, okay? We're looking at this guy here. It does have a cardinality of 0, minimum cardinality of 0. Now, it does have 2 children. It's the result of disjoining 2 formulas. One of them has a minimum cardinality of 0, and the other has a minimum cardinality of 2. What does that mean? That means if you look at this child, every instantiation that satisfies this child will have a cardinality of 2 or more. And in this particular guy, no, I could have things with cardinality 0. All right, now, the claim is I can minimize the circuit by taking it and transforming it to another circuit whose models are only the minimum cardinality models. The claim is I can do this by killing some edges in this circuit. And I highlighted a node for you to give you a hint. Give me an example edge that I need to kill to filter out those guys that will have more than a minimum cardinality. Thinking only of this circuit now. That's rooted at this node. Any suggestion? Okay, guys, it's simple. This node has 2 children. We're going to kill one of them. One of them has 0 and one of them has 2. Okay, so someone is saying kill the guy that has a cardinality of 2. Yes. And if I do that, I'm suppressing some models, but every model I'm suppressing is a bad guy, right? Because it has a cardinality that I'm not interested in. And if you look at this, you'll find there are 2 children that you have to kill, or 2 edges for these 2 nodes. And basically what you're doing is you're going to OR nodes and killing those children that have a cardinality higher than what is attained at the node. So this is 2 and 0. I'm killing this guy. Now, if you remove these edges, you get some dangling nodes that are no longer referenced. You remove them, and here's what you have. Now, the claim is this circuit, every model of this circuit has cardinality 1. I got rid of everything that has a higher cardinality by simply doing this operation, which is pretty straightforward, as you can see. Now, these queries and transformations in general are very difficult, and now they're becoming very easy in this particular case. And I'll show you now one more concept on this guy so that you further your intuition. Now, we have this notion of a subcircuit, which is a notion that's interesting because it shows you how to get a model for the circuit. So the subcircuit, you do it by, you start at the top. For every OR node, you pick one child, exactly one child. So in this case, we picked this, and then we got to this AND node. For AND nodes, you pick all children. Okay, so we picked both, and then you keep traversing. So in this OR node, we just picked this guy. And at this OR node, there's only one child. Okay, and then we got to this AND node, we picked both child. So you start at the top, and you traverse the circuit. Every time you visit an OR node, you pick exactly one of its children. And every time you visit an AND node, you pick up all of its children till you get to the leaves. And the result of this navigation in this case is this subcircuit, which represents a model of the formula. So in this case, this guy, not A, B, C, and D, is actually a model of this particular circuit. Now, I made choices here. When I visited an OR node, I picked one particular child. If I were to pick the children differently, I will get a different subcircuit And let's see what happens if we do things differently here. So instead of choosing this child, I chose that. And see what, but by the way, look at the model in this case. It has a cardinality of 1, right? Now let's do this guy here, then I get a different subcircuit and I get a different model, but still cardinality of 1. And the other choices I could have made is when I went down here, right? So here's one of them. And you can see now what is the model in this case corresponding to this subcircuit. And the very last thing is this guy here. And that's so basically 4 models corresponding to setting A to false in each one of them. Okay, so I want to make one more observation about model enumeration and how can you do model enumeration more generally in linear time. And in this knowledge compilation map, that paper that we posted, you're going to find many results that look like the one I'm going to show you. I'm going to show you this, and then we'll go to a summary table that shows you what can you do on decomposable negation normal form. So the idea here is you can enumerate models in Polytime. And I'm going to explain what's written here in just a second. But the idea is that you give me your circuit as a DNNF, and I want to construct a decision tree for it, because we know the decision tree captures the models of the formula. And the way I'm going to do it is I'm going to, just like we did before, I pick a variable X, and I say, let's set X to true. Okay, now what I'm going to do is, I don't know whether there are models below or not, and I don't want to do any work if there is no model. So I'm going to take delta, condition it on X, which I know I can do that efficiently. And then I'm going to do a sat test on this formula. Now, delta is DNNF. I can condition a DNNF on X true in linear time. And then I can check consistency in linear time. So I'm going to get 2 things, consistent or not. If it is not consistent, then I put a false here and I'm done. Okay. And then I go to this guy and say, let's try this guy. So now I'm going to go and do condition on not X. And let's say I get consistent. What does that mean? That means there are models below this node. So in this case, I pick a Y. And then similarly, I try. So maybe under this false, it will be inconsistent. That is delta given not X and not Y is inconsistent. But in this case, let's say delta given not X and Y is consistent, then I go and keep doing. So the point is, when you build this tree and you're done, the tree itself will be proportional to the number of models that you have. And in fact, it will enumerate them. It's just listing them for you. And the amount of work that I've done is no more than linear in the number of models. And it turns out what this guy says, this procedure really did not depend on DNNF in particular. All it needed is an ability to do conditioning and consistency in linear time. So any representation that allows you to do conditioning in linear time and allows you to do consistency in linear time can be used to enumerate models in polynomial time, output polynomial. And this paper that you have has a whole bunch of results that look like this, where it derives, given that you're able to do these things, you can do that. And then based on what we know about circuits, we know what else they can do and so on. All right, so here's the summary. And then I'm going to make a couple of notes on this table. This is the queries that we had in the original guide. And we saw that you can do consistency, you can do causal entailment, and you can do model enumeration. Now, the guys that are empty we can't do that. I'm going to comment on this in a little bit, because there's 2 different notions of I cannot do. But we can do these things here, and we've shown them. And as far as transformations, we showed also that we can do conditioning, that we can do existential quantification. So in the knowledge compilation map, forgetting is existential quantification. So this is single variable. You existentially quantify one variable, and this is you existentially quantify any number of variables. There is a difference. Some languages or some circuit types allow you to existentially quantify only one variable in linear time, but not a whole bunch of them. We can also look at the conjunction, disjunction, and negation. Now, one thing you can see here is, for these guys also, there is a distinction between, am I conjoining just 2 guys, or am I conjoining a whole bunch of them? The distinction matter. Bounded conjoin, think of it as like joining only a fixed number of things. Some languages allow you to conjoin just two things or a fixed number of things efficiently, but not an arbitrary. In this case, we can't do either of that in general. Disjunction is easy for DNNF, right? Because you can just put an OR node and you're good, right? You don't violate anything. Negation is not easy. Now, we showed the yeses, we didn't do the no's and why you can't do them, but I was gonna give you a hint of that next. A hint of how you can show a negative result. And you will find all of these in the paper that you have if you're interested, but we're not gonna do this here. This is too many things to remember, but I just want to give you an example of a negative result. And before I do that, let me tell you that there's two types of negative results. So if you look in the paper, you will find that when it says cannot do, you'll find two types of cannot do. Usually there is this check mark for something that can be done in Polytime. And if something cannot be done in Polytime, you'll see either this or that. This means cannot do, period. This means cannot do unless P equals NP. So that is done under some complexity assumption. Maybe that's too advanced for us, but when you look at the paper and you see these two circles in the tables, you should know you're going to see either this or this or that. So now I'm going to show you an example of a negative according to this, and maybe you can help me with this. The fact that it's hard. If you give me a whole bunch of DNNFs, D1, delta 1, delta 2, the claim, you cannot take these guys and generate a conjunction easily or in polynomial time and their sizes. Remember, these are all DNNF. To get something that looks like this in DNNF, that's hard. And the idea of these negative results is like, well, if you can do this, then you can do something that we know cannot be done. Okay, that's usually the structure of these proofs. So let's say you have someone claims they have a box. You give them an arbitrary number of DNNF circuits, and they bring back to you their conjunction as a DNNF in polynomial time. Suppose someone tells you, I do have that box. And then you tell them, no, you can't have that box, because if you have that box, you can solve this problem. And we know that this problem is not easy. So any ideas of how we can show this negative result? And I'm going to give you a hint. Sat on CNF. We know this is difficult. And the claim, if someone has a box that does what we mentioned, then you can tell that guy, oh, if you have that box, then you can solve SAT in polynomial time. Any suggestion? And let me make it a bit easier here. So the CNF is going to have clauses alpha 1 and alpha 2 and okay. Now this is the hint is becoming clearer and clearer. Right, so someone is saying basically, can you conjoin the CNF clauses into, yes. I mean, you can, these are clauses. So to take a clause is effectively already a DNNF. Why? Because it's a disjunction. So not X or Y or not Z. So to put this as a DNNF circuit, that's easy. So you can take every clause, convert it to a DNNF circuit, and then give them to the guy and say, conjoin them. And he will say, oh, I can do it in polynomial time. And he brings you back a circuit, a DNNF circuit that's equivalent to the original CNF. And now you do satisfiability on that. So if you had such a box, then you had a box to solve SAT on CNF in polytime. And that wouldn't be the case unless P equals NP. So this is an example negative result. I just want to end with one more property related to decomposability. I'm going to just sketch it for you. And this came later. This property was pretty influential. It's known as structured decomposability. It's a special case of decomposability. It was introduced also by in a paper with one of our past PhD students, not Pippa Strawat. I'll tell you what that property is, pretty intuitive, and I'll just mention one thing that it enabled that is not true for general decomposability, but it becomes true for structured decomposability, and that end up having a lot of implications. And then we will basically leave it at that. So this is the property that's known as structure decomposability. If you look at decomposability, look here, look at this AND node and that AND node. So in this case, you have AB here, and in this case, CD. Now, in this case, I have AC and I have BD. So the way the non-overlap is different, right? And if you want to think at this node as having ABCD and this node having ABCD, I split the variables differently. In structure decomposability, no, we constrain the way in which variables are decomposed. So in a situation like this, you will end up seeing AB here, CD, AB, and CD. And how does that happen? That happens by using something known as a V-tree. So the V-tree is just a binary tree, the leaves of which are the variables. Now you can pick any of these guys, and there's so many of them, but you have to pick one. And when you're building your circuit, you have to adhere to one of these. How do you adhere to it? You adhere to it in the following way. By making sure that in your circuit, every AND node maps to one of these nodes in the V-tree. Now, in this case, I must have binary AND nodes, only 2 children. So what does it mean that this is adhering to that node? That means one child of this AND node should have all of its variables in one subtree, and the other child must have all of its variable in the other subtree. Okay? You cannot just decompose variables arbitrarily. So this node adheres to that, and this node also adheres to it. And now as a result, you can see that these variables AC are on this subtree, and these variables here are on that subtree. And every other AND node should adhere to something. So you can see here what's going on here. All right. So you can't just have arbitrary decomposability. Your decomposability has to follow a scheme. And that scheme is called a V-tree for variable tree. Now, which variable tree do you use? The properties that we're going to talk about doesn't matter which one you use. But actually, the size of the circuit end up being influenced by that V-tree. This is a subject we're going to get to later when we talk about compilation, because if you want to compile a formula or a knowledge base into structured DNNF, you will need to pick up a good V-tree. Okay, now I just want to make one observation. So what's the big deal? What does this help us with? Well, if you have structured decomposability, and then you'll see that now you can conjoin 2 circuits in Polytime. You couldn't do this for a general decomposability. If you were to look at this table here, I cannot conjoin either an arbitrary number or a fixed number of circuits, DNF circuits. I cannot do that in Polytime, but now you can do it if you have structured decomposability, and that's a big deal. Let me show you quickly why, and then I'll show you one main application, and then we'll leave it at that. So why? Because if you try to conjoin now 2 circuits, you'll end up dealing with 4 cases, and they'll all end up being easy. So I'm just going to show you these cases, what they are, and sketch the algorithm quickly. If you're trying to conjoin 2 guys, this is a circuit. I don't know what's happening inside it, but this one is an OR. It has 2 children. If you're trying to conjoin them, that's always easy, right? So in this case, you go and say, okay, I will conjoin this with this, and I will conjoin this with that, and that's my result. Okay? So if you have the algorithm conjoin that can take 2 circuits and conjoin them, you use it this way. So you can always do the recursive call in this case. That's not hard. The hard part comes when you're actually doing 2 ANDs, all right? So I have this circuit, alpha and beta, this circuit, da. Let's call this circuit X and this circuit Y. I'm trying to conjoin them. And generally, that's hard if you have just decomposability. But if you have structured decomposability, you end up looking at only 3 cases, and all of them recurs nicely. So I'm just going to list them for you. You're not expected to know these details or remember them, but so that you just get an intuition of why, structured decomposability helps. Here's the first case. The first case is that those 2 circuits do not share variables, right? That's easy. I just put an AND and I'm done. Okay. The question is what happens when they share variables, and there you end up having to look only at 2 cases. because they're structured with respect to the same V3. One case is that the variables of this are all in here, in which case you just do this. You conjoin Y with that guy and put, and you're guaranteed to get decomposability. Remember, the tricky part here is to do this recursion while guaranteeing that there is no variable sharing. Okay, this is guaranteed no variable sharing. This is guaranteed no variable sharing. And it turns out the only other case you have to look at is if these two guys are, they adhere to the same V3 node, in which case you do that. So what really I showed you here is how to recursively break the conjoining of two ands or two ors into smaller things while guaranteeing decomposability. And you can only do this because these two guys adhere to the same V3. Okay, may not be immediately obvious. That's fine. I just want to give you the feel of what's going on here. And it turns out that this algorithm ends up having a quadratic complexity. So if the first circuit has size n, the other has size m, it's basically big O n of m. You can actually conjoin two structured decomposable circuits in quadratic time, and the result will be structured decomposable negation normal form circuit. So let's end this with one observation. How do you use this? One way you can use this is to compile formulas, right? So suppose I give you a CNF and I told you I want to compile the CNF into a structured decomposable circuit. Now that you have this algorithm, what do? You take your CNF and it has these clauses alpha 1, alpha n. You convert each clause into a circuit of this type. That should be easy. And then you just conjoin them one after the other. And this way you get, at the end, a structured DNNF that is equivalent to that CNF. Now, each step in this process is polynomial. But of course, as you repeat this process, the circuit may grow and grow. And what I just mentioned is known as bottom-up compilation. Later, we'll talk about how do you actually compile formulas. You're going to find that there's two kind of approaches, what's called top-down and bottom-up. And this would be an example of bottom-up. Top-down will be very related to the techniques we did earlier on SAT, but we're getting to this later. Okay, so today we focused quite a bit on decomposability. You know quite a bit on decomposable circuits now, and we looked at structured decomposability. Structured decomposability came about a decade after, and it does play an influential role. It gets used quite a bit because of its nice properties. What we look at next lecture is determinism, and you will see a whole bunch of new applications because determinism allows counting. So we enter into the world of probabilistic reasoning, and it will be a fascinating story. Then we'll do top-down compilation and then do two more circuit types after that. So folks, we're done for today. So thank you, and I will see you on Thursday.